Okay, so you're gonna know when you see an exponential growth or decay. You're gonna always know. The reason why is because you're gonna see this terminology, directly proportional, directly proportional. Anytime you see that, it's exponential growth and decay. That's the big one, okay? So what is directly proportional? Well, this. Remember, x is the independent variable, right? Y is the dependent variable, okay? So dy dx, which we know before is a rate, is a derivative, equals y, which is the dependent variable, right? K is what we call a constant of proportionality. It's something we're going to need to solve for, okay? It's a constant, right? It's a number, it's not a variable, so K is just a number. That's why you've seen some Ks in some of your assignments. You're like, why is there a K in there? Because we'd be seeing it. I knew we'd be seeing it, okay? So that's where it comes from. So the first thing we're going to do is something we've done before. Solve by separating. Solve by separating. Okay, so remind me, what's the first step when we're solving by separating?
Put y on the left and x on the right.
Yes, put y on the left, x on the right. Good. So we got dy over dx equals k, it's times y. And remember, k is not a variable, okay? So when we do that, what are we going to do? What are we going to get? You guys have done it many, many times, enough times already. I don't have to do the steps. What's going to happen when I move the x is on the right and y is on the left? What's going to be the left side? 1 over y, dy, right? And then what's going to be on the other side? K times dx, right? Yeah, k times dx, okay? Because I divide both sides by y, multiply both sides by dx. You guys have done that. That part's not new.
What if k is on the other side?
So k is a constant. Anytime we have a constant, we want to keep it on the right. So if it wasn't, we'd move it over. But it'll always be on the right. Today, it'll always be on the right, yeah. Okay? Second step, antiderivative, right? Okay. What is the antiderivative of 1 over y? Natural log of y, right? I'm going to put it in bars because it always has to be positive. What's the natural log of k dx? Kx, right? And then what else? Plus c. Yeah, plus c. Okay. We don't have a point, so I got nothing to plug in, right, for x and y. If we had a point, I'd plug it in. What was the last step? Solve for y, right? So this guy, how am I going to solve for y? How do I remove, because I want to get the natural log away. I want to get the natural log and pull it away, right? The only way to do that is by changing it to a exponent, right? So how do I do that? We're going to be doing a lot of that today. We're going to be doing a lot of this today. Really, this is how it's written, right? Really, it's natural log is just log with a base of e, right? So to change it from a log to an exponent, can't even spell, exponent, we use the loop, right? We use the loop trick, right? So we say e to this power equals this guy. So e to the kx plus c equals y. Okay? We've done that before. Nothing new, right? Today there's going to be a couple new things. First new thing is, you're going to see this a lot. So I'm going to change this up a little bit. So what's the one way to say this? How do I separate these powers here? Or why did I add these two? What's causing this addition part here? When do we add powers? In other words, when do we add powers? When do we subtract powers? When do we multiply powers? It's actually up here. Just coincidentally, this is what we're doing in math 3. When do we add powers? You see this one's add, multiply, subtract. The only time we add powers
Like powers together.
is when I have the same base and I'm adding the powers, right? That's why that's a plus. Well, to deconstruct it, I'm going to deconstruct it a little bit. And I'll tell you why, because it's going to help us today. So instead of that, I'm going to take it apart and I'm going to write it like that. Why am I doing that? Because it's going to help us today. First reason why I'm doing this is because this guy right here is your constant of proportionality. That's a constant. E is a number. C is a number, right? K is a number. X, we don't know though. So this guy over here is a variable. This guy is a variable still because it's got X. This guy is not. Okay? This guy is actually, I'm going to write it over here. Sometimes you'll see them not put that. Sometimes they'll put, instead of that, they'll put a capital C. Not a lowercase c, a capital C. What that is going to be our initial amount, which means nothing right now, but when we do the next problem, it's going to mean a lot. Okay? So sometimes you'll see this written as this way. They'll write capital C times e to the kx. It's the initial amount. Okay? All right. Okay. So what I want to do now is we're going to do the first problem. We're going to do the first problem. Okay? So I'm going to go slow on the first one and then because it's very similar to what we've been doing but a little bit different. Okay? So these problems are in context. You talk about bacteria. You talk about radium. Radium is an element. Okay, radium 226 is an element. Okay, it's on the element chart. It's on the table of elements. And then you talk about manufacturing companies selling TVs and stuff like that. Okay, so it's in context. It has a background. That's what I mean by that. Okay, so the first one, bacteria. Bacteria in a culture increased from 400 to 1,600 in 3 hours. Assuming that the rate of increase of the population is, here's our word, here's our buzzwords here, here's our phrase, directly proportional. That means we're going to use exponential growth and decay to the population. So the first thing, there's 2 variables there. What are the 2 variables that I'm talking about in this problem? There's 2 variables in this problem. What are they going to be? Of population of, you're right, population of bacteria, right?
And time.
And time. And time. In this case, it's hours, right? Which of those, here's my question, which of those is the independent and which of them is the dependent?
The bacteria is the independent.
So independent means I can't control it. Independent means, dependent means it's dependent on the independent. Time is always going to be your independent. Very rarely is time going to be dependent. Bacteria is dependent on time. As time goes on, it either goes up or goes down. In this case, it goes up. So this is the dependent. Okay, so first thing I'm going to do is set up my equation. But instead of using x's and y's, I want to make it more for this problem. So x is our independent. What was our independent? Time. So I'm going to use a lowercase t. So I'm going to use a lowercase t for independent x. Y was what?
The dependent.
Okay, but what was y? Bacteria, right? So I'm going to use a capital B. So instead of x and y, I'm going to use B for bacteria and T for time. Okay, so this is time, and this is bacteria. Okay, so dy over dx, right? What is y in this case? B or T? B. And T is time, right? K stays the same. And then it's K times Y, right? And what is Y in this case?
Bacteria.
Bacteria, B. Okay? That's our setup. Now we have to solve that. So what are we going to do to solve it?
Put B on the left and then T on the right.
Yep. Put everything, put the independent, the Y's on the left, and the dependent, or sorry, the dependent on the left, independent on the right. T is going to move to the right, B's are going to move to the left. So I'm going to multiply both sides by dt, divide both sides by b. You've done this before, the only difference is it was x and y instead of b's and t's. So I get 1 over b db equals k dt. First step done. Second step, antiderivative. What's the antiderivative of 1 over b? Natural log of b. Again, I'm keeping it in bars because it has to be positive. Bacteria is always going to be positive. You can't have negative bacteria. So the bars aren't really that important on this problem, but it's just good practice. Okay, so what's the antiderivative of the right side?
KX.
Not x, t, yeah, plus c, right? Yeah. Lowercase c, not uppercase c, lowercase c. All right. So what is it going to be? So how do I get b by itself?
Make it an exponent.
Make it an exponent, right? So what is the exponent going to be? Remember?
KT plus C.
Yeah, some of you can do this in your head, do it in your head. Some of you need to write it like this, do it. Whatever it needs to be so that you can see how to change it. So now I'm going to go. So it's going to be exactly like what the last one was. The only difference is it's going to be a B and a T instead of an X and a Y. Okay. And then I'm going to separate it again, just like I did the last time, e to the c times e to the kt. Okay. For me to answer A, I have to answer 2 more questions. I have to figure out what this guy is, and I have to figure out what k is. I have to figure out what those 2 variables are. If I figure out what those, well, the first one's not a variable, but if I can figure out what they are, then I've found the appropriate equation. But right now I have too many variables. I don't know what this is. It's a value. I don't know what it is. And I don't know what this is, so I have to solve for both of them. Okay? So to solve for them, I'm going to take a little bit of a sidestep. I'm going to write down what I know. TB. So what do I know about the bacteria?
It increases from 400 to 1,600 in 3 hours.
In 3 hours, it increases by that much, right? So T we'll say is hours. So I know in 3 hours, it's going to be 1,600, right? What is it going to be in 400? When is it going to be 400? How many hours? 0, yeah. What do we call this point? This point has a special name. What do we call this point here in terms of the problem? What does 0 mean? Initial amount, right? It's our initial amount. That is going to go right there. So B equals 400 times e to the kt. Because this is the initial amount. Right? Like I said, didn't mean anything on the last problem, but now it's starting to make a little more sense. How many bacteria did we start with? 600. Or sorry, 400. Now my last step is I have to solve for K. How am I going to solve for K? Because right now I have two unknowns. I have time and I have K. I have two unknowns. I got to solve for one of them first before I can find the other. I need K. So what's a way I can solve for K?
Maybe K is how much it's increasing.
Okay. I don't know that though. That's what I'm trying to figure out. It is. It's the constant proportionality. It's how fast is it increasing. But I don't know what that is now. How do I use what I have so far to figure that out?
Subtract 800 from 1,600.
Subtract 800?
Yeah.
Where'd you get 800 from?
Because if 0 is 400 and we want to get the growing.
Okay. I see what you're saying. So you're finding slope. Here's the problem. This is not linear. It's exponential. So yeah, so if I found the slope 1,600 minus 400 over 3 minus 0, that would work if it was linear. This is exponential. So exponential grows at a different rate. So yeah, it's a good try, but I can't do that. I can't use that. How can I find, so my question is, how can I find K? Here's my other question. Do I have some B's and T's? Where do I have them at? On the table, right? I got some on the table. I've already used the first one. That's how I came up with 400. I got another one. I'm going to plug this guy in and see what happens. So B is 1,600. And T is 3. So I have 1,600 equals 400 times e to the 3k. So in 3 hours, I should have 1,600 bacteria. That's what I plugged in. Now, I only got one variable. Okay. How can I solve for it? How do I solve for k? What's the first step I'm going to do? Not subtract, you're close.
Divide.
Since it's being multiplied, since 400 is being multiplied, you're going to divide by 400. Good. So we got e to the 3k. 400 goes into 1,600 4 times. Here comes the tricky part. not tricky, you've done it before. To get K down to Earth, K's up in the sky right now, right? To get it back down to Earth, I have to go this way.
Don't you have to like make it into like an L shape?
There you go, good job. You remember that from last year, right? So we use the loop when I want to go from a log to an exponent. But when I want to go the other way, I use what's called the L. And I'll show you. I'll show you exactly what that means. To do the L, okay, so I'm going to write it like this. The exponent's on the left. The L looks like this. It starts with a log. Log base of E. What is a log with a base of E called? A natural log. So in other words, it's a natural log. So natural log, okay, natural log of 4 equals 3K. That's how you get an exponent down on the ground. Okay? How do I get K by itself? Divide by 3. So K is 1/3 times the natural log of 4. Okay. So this guy here, I'm going to go and put in what I know. Okay. So B equals 400. E, I know what K is now. K is 1/3 times the natural log of 4 times T. That's my equation I'm going to use. So how did I do that? I solved by separating, right? You've done that before. Then I found out what the initial was, okay? And then I used the point to figure out what K is. Those are the things you need to do to find your equation, okay? Okay, so now we're going to use that guy. We're going to use that guy to answer the next question. It's a calculator question. All of these today that you have are calculator questions, okay? So these are all calculator-friendly questions. So now I got to find the number of bacteria at the end of 6 hours. So at the end of 6 hours, I have to figure out how much bacteria. So in other words, let me bring back my table that I had earlier. We know at 0 hours, it's 400, right? And then we know at 4 hours, it was 1,600, right? Or was it 3 hours? 3 hours, sorry, yeah, 3 hours. What they want to know is, okay, 6 hours, what's it going to be? Again, I know a lot of you want to say, okay, well, it grew by 1,200. Isn't it going to grow by 1,200 again because it's just double? That's if it's linear. This is not linear. Okay, this is not linear. Okay, this is an exponential. Okay? So what I'm going to do is I'm going to use my model or equation that I have earlier, right? B equals 400 times E to the 1/3 times natural log of 4 times T. That's the guy I came up with an A. I'm going to use that to figure out 6. So I'm just going to plug in 6 and see how much bacteria I get. Times 6. Once you do that, you go straight to your calculator. Okay?
So on this, we could use calculators?
Yes. For this section, it's calculator. All the questions are calculator friendly. The homework, the assignment that I'm going to give you in a few days, that'll be all calculator. Okay? So, let's see here. Here we go. Where's my calculator? There we go, that works. Okay, so calculator. These are the calculators I have in the back. They're not in the back yet right now, but they will be. It's Numworks, it's a calculator. The app, it's a free app. And these are the exact calculators I have in the back. If you have a graphing calculator, you can use it. If you have any calculator, you can use it. But this is the one I have in the back that you can use. So to do this one, I got to go 400 times E. So I'm going to go 400 times E to the 1/3, parentheses 1 divided by 3. Oops, I don't want that. Times the natural log, parentheses natural log of 4. And then times 6. 6,400. 6,400. Bacteria. Okay. After 6 hours, there'll be 6,400 bacteria. Okay. All right. All right, let's do the next one. So the last one grew. This one is going to die, decay. So radium-226 is an element, okay? So elements lose their mass at a rate that is, here we go, directly proportional to its mass. If its half-life is 1,590 years. Okay, so what is a half-life? You learn about, I think you talk about this in, I'm not sure biology, but definitely in chemistry. What is a half-life? There you go. Yeah, it's exactly what it is. Half of its life. It means it's going to retain half of its life after 1,590 years. So after 1,590 years have passed, it maintains half of what it started with. And then in another 1,590 years, it retains half of what it had after that. Okay? That's what it is. So it starts with a mass of 100, right? So in 1,590 years, how many milligrams are going to be left? 50. And then in another 1,590 years, how many milligrams are going to be left? 25, and so on and so forth, right? And if you keep doing it that way, you'll always have something left. You'll always have something left. There will always be something left. Because anytime you divide, you're always going to get something left. If you keep dividing a pizza up in two, up in half, and up in half, you'll always have some pizza left. Okay? Okay, so, and if we start with a sample of radium-226 with a mass of 100 milligrams, find the formula for the mass. So we need to find the equation first. Okay? All right, so here we go. What's the independent, what's the dependent?
The dependent is the radium.
Okay.
And the independent is the years.
Independent is years, right? So yeah, independent is years. So we'll use time again, right? So time. Let me see, let me make a little table here. I'm not going to fill out the table yet, but I will in a second. And then radium, or mass, however you want to say. You can call it radium, you can call it mass, whatever you want. Okay, I'll call it capital R for radium. T is in years, R is in milligrams. Okay? So it's going to be D what over D what equals K times what? dr over dt equals K times R. Okay, so what is it going to be? What's our next step? If it said x and y instead of r and t, what would be our next step? Yeah. Move the r's to the left and t's to the right. One over r equals dr. Oops, not equals. Equals k times dt, or k dt, right? Okay. What's the antiderivative of 1 over r? Natural log of r. Hopefully this is sounding familiar, because you're going to do this quite a bit. And if you realize it, you can skip this step, okay? I haven't skipped it because I don't know if we're there yet, but you can skip it if you want.
You could just put log e.
Skip to the end. Yeah. What's going to be our next step?
Do the loop trick.
Do the loop trick, right? E to the kt plus c equals r. R equals e to the c times e to the kt, right? So yeah, absolutely. You don't have to do this. We've done this before. All of this mess here, you don't have to do if you don't want to. You can skip right to there because you know what it's going to lead to. Instead of x's and y's, it's going to be r's and t's, right? But again, if you're not sure, keep doing this. Take an extra few minutes to do it, okay? All right, so let me move this guy back up. R equals e to the c times e to the kt. All right, so now let's fill out our table. What do we know about our table? Yep. So after 1,590 years, it's going to retain half of its mass. And what was half of its mass? Or what's going to be left? 50, right? And then in another 1,590 years, it's going to have 25, and so on and so forth, right?
0 is 2.
You're close.
Because it's
0 is?
negative 226.
No. 100. That's what I start with, right?
So what is the 226? Wait a minute.
That's just the name of it. Radium-226 is the name of the element. Yeah, it's just the name. All right. So what do I do with that first? What can I utilize first? Starts with an I.
Initial.
Initial amount, right? What was the initial amount? 100. So this guy is going to be 100. Last step, solve for K. How did I solve for K the last time? Plug in R and T. Plug in the R's and T's that we know. I'm going to use the second point. So when there's 50 radium left, 100 times E to the K times 1,590. How do I solve for k now? What's the first step I'm going to do? Divide by 100. Divide by 100. Good. That leaves half, right? 0.5. E to the k times 1 point, or 1, not 1 point, 1,590. How do I get k down to the ground? The L trick. So to use the L trick, you have to have the exponent on the left side. So just move it over to the left. So the natural log of 0.5 equals 1,590 times k. Running out of space, so I'll put it here. The natural log of 0.5 equals 1,590 times k. Solve for k. How do I get k by itself? Divide both sides by 1,590. So instead of dividing, I'm just going to put a big fraction. Okay. Last step, put k back in. So R equals 100 times E to the 1 over 1,590 times natural log of 0.5 times t. That's our formula we're going to use. So what I want you to do is do part B now. We did the hard part. Part B is the easy part. How many mass would be there after 10 years or 1,000 years? How many milligrams are left after 1,000 years? Natural log of 0.5 times 1,000, no? Okay. Not 1,000, sorry, it's 100. 100 e to the 1 over 1,590 times natural log of 0.5 times 1,000. Usually go 3 spaces. I'd say 3 spaces past the decimal is safe unless they tell you to go differently. So 6.4 64.666 milligrams. Okay. Last step, does it make sense? Does that number make sense? Should it be more, should it be less, or does that about right? How do you know? Look at the table. That number fits in between 100 and 500, or no, 150. How many years was it? Does 1,000 fit in the same spot? Yeah, fits right. A little bit closer to 1,590, so I would expect a number closer to 50 than 100. Yeah, it works. Okay. Part C, how do I do part C? If you tell me how to do it, I will help you with it. How do I do part C? Or how is it different than the question we just asked? Yeah, changing variables, right? This is not T, this is R. So you got to plug that in for R. So we get 30 equals 100 e to the 1 over 1,590 times natural log of 0.5 times t. This time we got to solve for t instead of r. What do we do first to solve for t? Divide by 100. 30 divided by 100 is 0.3. What's the next step? L trick, yep, L trick. So when you do the L trick, you're going to get natural log of 0.3 equals 1 over 1,590 times the natural log of 0.5 times t. And then I did the L. How do I solve for t? Divide. Divide by what I don't want. And that's when you go to your calculator. Division, oops, no. The natural log of 0.3 divided by 1 over times the natural log of 0.5. The natural log of 0.5. No, I don't want that there. The natural log of 0.5. Nope, don't want that. Keeps doing what I don't want it to do. Let's see. Wait, yeah, no, that was okay. Yeah, that was okay, sorry. So I get 2,761, wait. Yeah, 2,761.776 or 775. 2,761.775 761.775.
And will we have to put years?
So T was years, right? Years. That's how long it would take for 30 to be left. Again, you should always, always, always ask yourself, does it make sense? Does it make sense? Again, 2,761 is right here in between. 30 is in between. So yeah, it makes sense. Okay. All right. Yeah, I'm not going to go on to the last one. We'll do the last one tomorrow, and if we have some time, I'm going to give you some more problems, and I'll get the calculators out so that you can practice with them. Because you can use calculators. This is one of the only sections where you can. It's 100% calculator friendly.